right? And so our first topic today is going to be what are called buffers. All right, so first of all, a buffer is a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid. All right, so we talked about weak acids and weak bases last class period. We talked about how we find conjugate acids of our bases and how we find conjugate bases of our acids. If we took a weak acid and its conjugate base and we mixed them together, we would create what we call a buffer solution. Okay? And buffer solutions are really special because buffer solutions resist changes in pH. Okay, these buffers play like an outsized role in especially biology and biochemistry. I was a biochemist, that's what I have my degree in. Every single reaction that I ever did took place in a buffer. Because in biology, your tissues like to be at a very specific pH. Actually, your blood likes to be at a certain pH, different from your lung tissues, different from your muscle tissues, et cetera, et cetera. Your body's always trying to maintain a very specific pH, and changes to that pH will damage those cells. All right, so your body employs these buffer systems that make it so that things that happen, chemical reactions that happen in that cell, don't end up changing the pH of that solution. All right, a really simple example is ATP. Who's heard of ATP before? Right, the energy currency of the cell. Well, it turns out that the generation of ATP will necessarily create like an acid in the process. It's just a byproduct of the creation of those ATP molecules. And the cell needs energy. It needs to create those ATP molecules, but it can't have those hydronium ions being created actually change the pH of the cell, or it's going to mess up the whole chemistry balance going on there, right? So all your cells have these buffer systems in there, and their goals are to resist changes in pH. And basically what we're going to do is we're going to sort of talk about these buffer systems, how to calculate the pH of a buffer system, and then I'll prove to you this whole resisting changes in pH business, okay? So first of all, let's just take an example of a buffer solution. All right, what we're going to do is we're going to make a buffer. Whoops. And we're going to do this by combining a weak acid. We're going to use benzoic acid. All right. And it's I'll put the formula for benzoic acid down here, C7H5O2H. Wow. And its conjugate base. All right, everybody take a second. If this is my formula for benzoic acid here, what's its conjugate bases formula going to be? All right, remember acids, they're going to donate those protons. So I'm going to take my acid formula, I'm going to decrease the number of hydrogens. And what else am I going to have to do? Give that a negative charge. All right. Our buffer is going to, so we're going to mix these two things together. We're going to make our benzoic acid concentration equal to 0.75 molar and our conjugate base concentration equal to 0.5 molar. All right, and what we're going to calculate is the pH of our buffer. Okay, so let's just say, what is the pH? All right, so we're going to start in a familiar place. This whole scheme that we laid out last time with weak acids and weak bases, where the first thing you're going to do is you're going to give me this acid dissociation equation. All right, as with our other discussion of weak acids and bases, these are going to be equilibrium problems. So we also need that Ka expression. And how do we go about solving our equilibrium problems? What do we use? An ice table. So same steps we're going to need here. All right, so I'm going to give you guys a little bit of a head start here. Try to give me the acid dissociation equation of benzoic acid. And I'm going to kind of quietly fill in, so if you get stuck, you can look up here. All right, but given what we discussed last class period, really 2 class periods ago about these acid dissociation equations, but then last class period about weak acids, see if you can't give me these 3 pieces of information here. All right, so remember my acid dissociation equation is where I take my acid and I add it to water. Water's always in our acid dissociation equation. And our acids will dissociate into hydronium ions and whatever their conjugate base is. All right, so my Ka is just my equilibrium constant for this acid dissociation equation. It's Ka because it's an acid dissociation equilibrium constant. Products over reactants, but I get to omit that liquid water. And now I'm going to build my ice table. All right, so we got our ice table built. According to my problem here, what is my initial concentration of my benzoic acid? That's 0.75 molar. All right, and previously we've been doing all these problems where we don't have any product yet in solution. But the basis of these buffer problems is what else am I starting out with initially in this solution? My conjugate base. My conjugate base has 0.5 molar in it, so I don't have any reaction that has happened yet, but I do start out with an initial concentration of 0.5 molar in that conjugate base. All right, our change box is always that variable x, because this is what we're trying to figure out, how much of this reaction has occurred. All right, but I got to worry about my sign here. My benzoic acid is a reactant, so that's going to have what sign? That negative sign. My products have that positive sign. And then I get my E box by doing what? I'm going to take this row, add this row. All right, sum up those first two rows. So 0.75 minus x, x, and 0.5 plus x. Okay. So I have my equilibrium box here. I can then take this, plug it back into my equilibrium expression for my concentration of benzoic acid, since that's my equilibrium concentration of benzoic acid. I can take X, plug it back in to my box for my hydronium ion concentration, and then for my conjugate base here, what we call benzoate, plug that in up there. What other key piece of information am I going to need to find that value of X though? That Ka value, right? And where do we get Ka from? Everybody's got that table memorized, right? No, I'm kidding. Obviously, that's ridiculous. Nobody would ever do that. It's going to be given to you on your exam, right? Again, on your constants page. So we're going to go to our constants page here. We're going to find that benzoic acid. Whoops. All right, and we're going to make note of that equilibrium constant, 6.5 times 10 to the negative 5. Okay? Now, if I'm after the pH of this solution, which one of these concentrations do I care about here? Which color? Green, blue, or orange? For pH. How do we calculate the pH of a solution? The negative log of H3O, right? So if I'm trying to find the pH, I need this value here. Okay? So let's go ahead, plug these in. All right. We have, I'm going to leave it as Ka for right now because I'm going to do a little algebra and it's going to make my life easier. X times 0.50 plus X over 0.75 minus X. All right, I took this, plugged it in up here, took this, plugged it in up here, took this, plugged it in down here. Boom. All right. Now, as we said last time, we had this small x approximation that we were using. Okay? The idea that this equilibrium constant, 6.5 times 10 to the negative 5, is not very big. Meaning this reaction does not favor the reactants, does not favor the products very much at all. It actually favors the reactants. Not only that, but I'm starting out this reaction with some product already in this solution. So that's going to shift the equilibrium even more in favor of that reactant. So we got some good news here. All right, so 4 buffers. That small x approximation is always valid. All right, now I can't set this x to 0. You can convince yourself that that would just break down the entire equation here, right? It would mean that Ka is equal to 0. That doesn't make any sense. But the small x approximation says that 0.5 plus x is basically just 0.5, and 0.75 minus x is basically just 0.75 because x is so teeny tiny small, right? Think about it. X is like 0.00001. It's not going to change the value of those numbers very much at all, which means that this simplifies to x times 0.5 over 0.75. All right, and we could stop here and we could solve for x, and that would be great. But we could simplify things a little bit, at least to the point where we don't have to do an ICE table every single time we want to find a solution of a buffer. Okay? So what we're going to do is we're going to take our equation here, and we're going to rearrange it. And this is what's called the Henderson-Hasselbalch equation. All right, so we're going to take our original equation here. And as we said, what we're interested in is that concentration of our acid, right? That's what's going to allow us to find our pH. So let's just rearrange this equation so that we get our concentration of acid all by itself. All right, I'm going to multiply both sides by my acid concentration. Come on. Okay, so this gives me my acid concentration over that conjugate base concentration times my equilibrium constant equals my hydronium concentration. All right, but let's go a step further. We're not actually after hydronium ion concentration. We're after our pH. So let's go ahead and we're going to take the negative log of both sides of this equation. Okay? The negative log of the hydronium concentration is the pH of our solution. All right, and then we're going to use this same, what would it be called? An identity that we used before, where in the magical world of logarithms, multiplication becomes addition. Remember, we used this before, the idea of the log of A times B is the same thing as the log of A plus the log of B. All right, so this becomes the negative log of our acid over our base. We're going to keep those together. Plus the negative log of our Ka. All right? Now, this should be the equilibrium concentration of our conjugate acid and our conjugate base. But remember, we just said that our small x approximation is always valid. So our equilibrium concentration of our acid, if we use that small x approximation, is just equal to its initial concentration. Likewise, the equilibrium concentration of our conjugate base, if we use that small x approximation, is just equal to its initial concentration. All right, so we don't even have to figure out what our equilibrium concentrations are. We can just use those initial concentrations from our problem. So to figure out the pH of our solution, we're just going to take the negative log of our acid concentration from the problem divided by our conjugate base concentration from the problem. I forgot a minus sign here. Plus the negative log of our the negative log of our Ka, and we'll have the pH of that buffer solution. All right, now we are going to do some fancy rearranging here, much like we called the negative log of hydronium pH, the negative log of hydroxide POH. We call the negative log of Ka the pKa of that solution, of that weak acid. All right, and we're going to use one more fancy log identity here that says that the log of A divided by B is the same thing as the negative log of B over A. So if we flip these two, we get to drop that negative sign. All right, so this will become the log of, instead of acid over base, we get the log of our base that we had initially, divided by the concentration of our acid that we had initially. This plus the pKa, which is the negative log of that Ka value, will give us the pH of our solution, and this is what we call the Henderson-Hasselbalch equation. All right, so basically, we didn't have to do this ice table step. Now that we have our Henderson-Hasselbalch equation, we had to do it because we had to prove that it works, all right? But now that we have our Henderson-Hasselbalch equation, we don't have to do the long way here. We get to skip writing out our chemical equation and our Ka equation and writing out our ice table. We just get to plug that information from our problem into our Henderson-Hasselbalch equation. So given this problem here, everybody take a second, and that Ka value that we looked up, which was 6.5 times 10 to the negative 5, everybody take a second and calculate the pH of this solution, of our buffer solution. Sure. All right, so importantly, which one of these was my base? The 0.75 or the 0.5 molar? This one's my acid. This one's my conjugate base, right? After that acid has donated that proton. So in my equation here, I'm going to do the log of 0.50 divided by my initial acid concentration of 0.5 plus the pKa. What's the pKa again? pKa is the negative log of that Ka value, so the negative log of 6.5 times 10 to the negative 5. All right, punch that into my calculator, and we're going to be lazy with our sig figs and just do 2 decimal places. a pH of 4.01. All right, so our Henderson-Hasselbalch equation here allows us to skip all that ice table business, just plug those initial values into our equation here along with the negative log of the Ka of that weak acid, and we get our pH of our solution. Okay, so in our initial notes of buffers, let's just note we have this special equation here. Our Henderson-Hasselbalch equation, our pH equals our pKa plus the log of base over acid. All right, there's one thing that we have to be really careful about for this Henderson-Hasselbalch equation, and that is that we don't use it just like willy-nilly for every acid and base problem. So we're going to make a special note here that this equation works only for buffers. It doesn't work for any random mixture of acids and bases. It has to be a weak acid and its conjugate base, or a weak base and its conjugate acid. If that's the case, then we get to use our Henderson-Hasselbalch equation here. All right, there's another important caveat to buffers, which we call an effective buffer range. And that is that this weak acid conjugate based mixture, it's not resistant at pHs just at any old pH. All right? The pH of your solution has to be within 1 unit of the pKa of that buffer system in order for that buffer to be effective, aka effectively resist changes to pH. And in fact, a buffer works best when the pH is at its pKa value. All right, but you got to be within that range for your buffer to effectively resist changes in pH. Cool. All right, so let's now prove that buffers resist changes in pH. So first we're going to compare a non-buffered system, aka just straight up water. All right, and this is going to be without any acid added. What's the pH of water without any acid or base in there? Neutral, right? So it's that pH of 7. And now I want you to add 0.1 molar HCl. This is our strong acid. So everybody's going to take a second and calculate the pH. Oh, let's do a little bit smaller. 0.01, sorry. What does that matter? 0.01 molar. Okay, everybody's going to take a second and calculate the pH of a 0.01 molar solution of hydrochloric acid. All right, what we get? For $1 million, what's the pH of this solution? 2. Okay, great. So remember, because how do we know what this is? Because, okay, importantly, this is a strong acid. And as we've established, that means that the concentration of that strong acid initially is going to equal the concentration of hydronium at equilibrium. So that means in order to get the pH, I'm just going to take the negative log of that 0.01, which gives me a pH of 2. All right, so if we add 0.01 molar HCl to water, we see a drop in our pH of -5. All right, the change in our pH is -5. All right, but now we're going to do the same thing, but with our buffer solution here. Our buffer solution, we're just going to stick with the same buffer solution as our example here. This is our buffer that has a concentration of our weak acid, benzoic acid, equal to 0.75 molar, and our concentration of that conjugate base equal to 0.5 molar. All right, now without any of that strong acid added, we just calculated that its pH would be 4.01. All right, that was the calculation that we just did using our Henderson-Hasselbalch equation. But now we're going to take this buffer and we're going to add that 0.01 molar HCl. And we're going to calculate what its concentration is. We're going to see if it indeed has that same big change in pH that we saw from adding this amount of acid to neutral water. All right, we're going to calculate this here. This will be our first example, and we're going to do this quite a bit going forward here, of combining acids and bases. All right, and I guess let's be specific here. That's broad. Combining acids and bases. This specific example will be a strong acid plus a buffer. Okay, so what we're going to do here, we're going to take our same buffer. We have a buffer with that benzoic acid concentration equal to 0.75 molar, and that conjugate benzoate equal to 0.5 molar. And we're going to combine with HCl to a concentration equal to 0.01 molar. All right. Now, unfortunately, we can't shortcut this one, at least not quite yet. All right, we're going to have to keep track of how much acid-base reaction occurs using an ice table here. But first thing we got to do is figure out what acid-base reaction occurs. All right, so let's ask, will HCl react with our acid benzoic acid? Or its conjugate base, all right, both of them are present in this buffer solution, right? I got both my acid floating around and that conjugate base floating around. I'm going to add HCl, a strong acid, to it. So let's take a vote here. Who thinks it's going to add, HCl is going to react with our acid, benzoic acid? And who thinks it's going to react with our base, this benzoate, our conjugate base? Okay, great, yeah. So it's going to react with our base. So we need our acid-base reaction. Notice this is not an acid dissociation reaction. I'm not reacting my acid with water. I'm reacting my acid, HCl, with my base in this mixture. That's C7H5O2. All right, and given what we've discussed about these acid-base reactions, you should know how to give me the formula for the conjugates of my acid and my base. What's my conjugate base? What's my conjugate acid? Right? So finish this chemical equation here for our acid-base reaction. All right, my acid is going to lose a hydrogen, and my base is going to gain a hydrogen. Okay, and in order to keep track of how much of this reaction has occurred, we're again going to use an ice table. All right, so everybody take a second. Let's build ourselves an ice table to work with. All right, I want you to take a second and fill out this ice table given the problem that we laid out here. and I'm combining my 0.1 molar HCl with my 0.5 molar of my conjugate base. I don't have any chloride yet because no reaction has occurred, but do I have any of my weak acid in there? Yes, because this is my buffer solution, right? I had some of that when I started out. So that's my 0.75 molar. My C box, that variable, what's going to be the sign for HCl? My reactants are going to decrease in concentration. My products are going to increase in concentration. And then how do I get that E box? I sum up those first two rows, so 0.01 minus X, 0.50 minus X, X, and 0.75 plus X. All right, and as always, we're trying to solve for our ice table. Solve for that value of X here. But we got a problem, all right? This is not a Ka expression, all right? Rather, this is not an acid dissociation reaction. This is not a reaction that we have an equilibrium constant for that we can look up on our table, right? This is not reacting an acid with water, creating those hydronium ions. This is reacting an acid with a base, okay? So how are we going to solve for this one here? Well, importantly, what do we know about HCl? It's a strong acid, all right? And we're going to have this very simple principle that we're going to use for when we mix our strong acids and our buffers, really when we mix our strong acids with anything, as well as strong bases. There's going to be this little phrase that we're going to remember over and over again, which is that all of the strong will react. All right, 100% of the HCl that you put in there is going to react with that conjugate base. All right, so then at equilibrium, how much HCl will be left over? If all of it reacts? 0. All right, so if this takes on a value of 0, that allows us to solve for our value of X. Right, 0.01 minus X has to equal 0. I believe in us. We can do this in our heads here. What's the value of X going to have to be? X is going to have to be that 0.01. All right. So now we're going to make what I call an ICES table, where you're going to solve for that equilibrium box by plugging in the value of X underneath here. S for solve, where you're going to solve that equilibrium box by plugging in the value of X here. All right, so I'm going to take my 0.5 and I'm going to subtract that X value of 0.01, leaving me with a value of 0.49. X is that 0.01, and 0.75 plus X is 0.76. All right, so now we got to figure out what the pH of this solution is, right? So let's take a look at what we have in this solution as this reaction reaches equilibrium. We have a mixture of our conjugate base, chloride ions, and our weak acid here. Okay, so how are we going to solve for the pH of this solution? Well, there's a really important relationship that we laid out last time. All right, so we're going to take a step back here. Remember we were talking about the relationship between Ka and Kb, those equilibrium constants. Remember, a large Ka value means a strong acid, a reaction that goes all the way to completion, right? A small Ka value, a weak acid. And we talked about how Ka times Kb equals Kw. All right, that was the last thing that we laid out at the end of last class period. But what do we know about Kw? Is that a variable? No, it always takes on one value. And what is that value? 10 to the negative 14. So this is a constant. Which means that if I have a very large Ka value, my Kb value has to be really tiny because it's got to equal that same constant number. Or if I have a very large Kb value, my Ka value has to be really tiny. Because again, when we multiply them together, they have to equal that same constant value. So what we'll see is there's this inverse relationship between the strength of an acid and the strength of its conjugate base. Okay? So let's just do some simple examples here. We're going to make a little table. This will be good practice for our conjugate pairs. I'm going to put down some acids, and you're going to give me their conjugate bases. All right, HNO3, if I'm going to do my conjugate base, I'm going to take away a hydrogen. I'm going to decrease its charge. Same thing with this one. I'm going to take away a hydrogen. Importantly, I'm going to take away the hydrogen from the front, decrease its charge. And then water's conjugate base is special. It's got a special name. What is it? Hydroxide. Okay. What do we know about HNO3, nitric acid? It's a strong acid. All right, that's on our list of 6 strong acids that we just got to know. HNO3, one of our strong acids. What do we know about this thing here? Is it on our list? No, so that means it's a weak acid. And what do we know about water? If I have water, what's its pH? 7. So this is an order of increasing acid strength here. All right, whereas nitric acid is a strong acid, and this thing here, acetic acid, is a weak acid, and water is neutral. All right, but if we look on the opposite side, what do we know about water's conjugate base, hydroxide? What do we classify that as? Strong base. All right, hydroxide. There are truthfully other strong bases out there, but hydroxide is the one that I told you need to be able to recognize for this course as that category of strong base. All right? The conjugate base of a weak acid is itself a weak base. All right, and just like the conjugate of something neutral was strong, the conjugate of something strong is itself neutral. So these nitrate ions here, they don't influence the pH at all. The conjugate of a strong acid does not influence the pH of a solution at all. All right, so we just want to make note here because this is going to be really important. Conjugate of strong is neutral. The conjugate of weak is itself weak. All right, so where am I going with this? Let's go back up here. We are concerned about the pH of this solution here, right? We're at equilibrium, so we no longer have any hydrochloric acid in this solution. All we have is our conjugate base, chloride ions, and our weak acid here. All right? But one of these isn't going to influence the pH of that solution at all. Which one is it? The chloride ions. And why not? Because it's the conjugate of something strong. So even though there's chloride ions floating around in this solution, this will not influence the pH of this solution. All right, because again, the conjugate of a strong acid is neutral. Meaning it doesn't influence the pH of your solution. So then, if I'm going to ignore that, really what I have is a mixture of a weak acid and its conjugate base, and we call those, name of the lecture today, buffers, okay? And if we have a buffer solution, we get to use what? Henderson-Hasselbalch. Yes, the Henderson-Hasselbalch equation. Okay, great. So everybody take a second, use the Henderson-Hasselbalch equation, and tell me what the pH of my new solution is here. 6.5 times 10 to the negative 5, yeah. 6.5 times 10 to the 8. We're keeping the same buffer system here, so same as last time. Negative log of the Ka is the pK. So the P always means negative log. All right, so the pKa, the negative log of that Ka value, we're just keeping the same buffer system, so it's the same one that we looked up before. That's 6.5 times 10 to the negative 5. Plus the log of my concentration of base. So this is the one place, or this is one place that we have to be really careful. Which one is going to be my base here? The 4.49 or the 0.76? Right? Here's my acid. Here is its conjugate base. So I'm going to need that 0.49 in the numerator and the 0.76 in the denominator. right, so let's just round this off to 2 decimal places like we did before. The pH here is 3.996, which we round to 2 decimal places, 4.00. 3.996. I just said 2 decimal places. We don't keep track of sig figs for these types of problems. So I'll tell you in your homework, like, enter this many decimal places. Okay? So again, the whole point was where we were going to compare. We knew what our buffer's pH was before we added any strong acid. Then we added that 0.1 molar strong acid. Did its pH decrease? Did it decrease anywhere near as much as it did when we added that strong base to water? Right? The change was 5 units when we were adding it to water. When we add it to buffer, it goes from 4.01 to 4.00. Right? Our delta pH here is just negative 0.01. All right? So again, buffers resist these changes in pH. If we just had water in our cells, any amount of acid that was created would have a big increase in the pH of that cell. But because we have these buffer systems, it's not like the pH doesn't change at all. Don't get me wrong. It resists these changes in pH, right? Meaning that our changes in pH are much less than it would be without that buffer system. Okay? Cool. All right, so we're going to practice this one more time here. We're going to pick a different buffer system here. I'm going to make a buffer system with butanoic acid here. Okay, so everybody take a second to copy down our relative our relevant Ka value for butanoic acid. Okay. All right, we're going to prepare a buffer solution with a concentration of our butanoic acid. You get a 0.6 molar. And our concentration of its conjugate base equal to 0.3 molar. I want to know what is the pH. All right, in case you missed it, I'll tell you that relevant Ka value was 1.5 times 10 to the negative 5. All right, and then you're going to tell me the pH if we combine it with our strong base, sodium hydroxide. All right, so first we have a buffer solution. So I get to use my Henderson-Hasselbalch equation. All right, importantly, my base is going to be my conjugate here, got the negative sign, doesn't have the hydrogen. My acids got the hydrogen, no negative sign. All right, so that's why I do my 0.63 over 0.46. Base over acid, I get a pH of 4.96. Okay, so now we're going to combine this buffer system with our sodium hydroxide here. What do we know about sodium hydroxide? Strong base. So which one is it going to react with, the acid or the base in this buffer? The acid. All right. So I'm going to do my chemical formula here. All right, and real quick, I want to stop right here. And this is something that I even tell my organic chemistry students, which is when you see sodium in an ionic compound, it's really important to understand it's not doing a damn thing in any chemical reaction. The only thing sodium's ions ever do is just sit there and float around all by themselves. They're never involved in a chemical reaction. They're always playing this role of what we call a spectator ion. They're floating around, they're watching stuff happen. If we could buy just hydroxide all by itself, we would. It's just impossible to have a beaker of just negative charge. It's got to have that counter ion there. That's what the sodium is doing. But whenever I see sodium in these ionic compounds, all right, with my acid-base reaction, I'm just going to erase it and replace it with a negative charge, because that's really what my base is. The sodium's not really doing anything. All right, if you really wanted to keep it there, I can show you how you would do it, but I think it's more confusing than it's worth because it's not actually involved in the chemical reaction at all. This is my acid-base reaction. And now we need an ice table to take care of it all. So we're not doing, we're going to see that it doesn't matter. You could have omitted it because it's neutral. But we're not doing an equilibrium expression. We're not plugging it back into an equilibrium expression. So we can, but I'm going to get to the point where I'm basically going to be like, we didn't have to do that. It doesn't matter, right? Because what do we know about water? Acidic, basic, or neutral? So then it doesn't matter how much is formed in this reaction. All right, so I have my ice table here. How am I supposed to solve for my value of x? If I want to put my extra little ices row in here, which one of these do I know at equilibrium? The OH, right? Because all of the strong will react, all right? So that means if all that strong reacts, I have none of it left over, and my value for x is that 0.02. All right, so filling in the rest of my solve row here, 0.46 minus 0.02 is 0.44. X is just 0.02. And 0.63 plus 0.02 is 0.65. All right, and just like before, we have none of this base left over. But if I'm concerned with my pH of the solution, there's one other thing that I don't really care about, and what's that? My neutral water, not going to influence the pH of my system at all. So again, I just am left with a buffer system that has 0.44 of my acid and 0.65 of its conjugate base, which I should be good, has a minus sign there. And in order to do my pH, I'm just going to put this into my Henderson-Hasselbalch equation again, because we have a buffer system, so we can Henderson-Hasselbalch it. Plus the log of my base, that's the 0.65. My 0.44. All right, and my pH is now 4.99. So we originally started with a pH of our buffer of 4.96. We added this strong base. It increased, but only a little bit to 4.99, right? So again, these buffer systems will resist changes to pH. All right, we have our first little bit introduction here into how we combine acids and bases using these ice tables. And we're going to pick up with that and do more on it next week.